talk about a topic which is sort of related to the morning's discussion, but the design area and the exact topic is completely different. But the target objective remains the same. So, in the morning session, we talked about a method called power getting, which is also important for the low power technology as well as for the reduction of the supply noise, which we have seen. When we have discussed there, if you can recall, we discussed about a terminology called clock getting, right? So clock getting can be incorporated in a system where clock is needed. And if I talk about any system or subsystem, clock is an important parameter for the synchronization of operation between many blocks. So fundamentally, what we know about a clock is it is generated by a quartz crystal, right? But if quartz crystal oscillates, it generates a frequency not more than 120 to 130 megahertz. I think as per the latest report of Core i9 processor, the quartz crystal might be generating up to 133 megahertz. But you see the processors are working at a frequency of 2 gigahertz to 4 gigahertz, 4.5 gigahertz, like that. If you think of a desktop with high-end processor, they are working at around 4.5 gigahertz. But in laptop, we are still around 2 to 2.5 or 2.8 gigahertz, right? So a basic question comes, there will be an way uh, by which we are converting that 125 or 130 megahertz to 2 gigahertz or 4 gigahertz as per the requirement of the logical core. Right? Fundamentally, we know that the circuit which does this particular job is nothing but a PLF, which is phase lock low. Right? Now, the point is, the moment you are converting from a low frequency to high frequency and you are allowing that high frequency to directly hit your device, uh, the similar situation comes up which I explained in the morning session. All right. So in the morning session, we discussed about a situation that you are sleeping and someone is trying to wake you up instantly. And what was the resultant? The resultant is suddenly you wake up and you are not understanding what's to be done. And we have discussed that why that is happening. This is because of a sudden rush of current. But the same phenomena can come over here also. Now think power is continuously connected. That was the power getting, right? We are making switch on or switch off. Now here we are considering that power is always connected. We are not dealing with power getting. But the point is, if it is a synchronous system where a lot of subblocks are there, if I have to build a synchronization, I need to hit it by a clock. Otherwise, it will not work. Now, the point is the operation can be done by a clock of 100 megahertz or 200 megahertz. The operation can also be done by 2 gigahertz if the design is appropriate. So now we are talking about the difference between running a system at a frequency of 200 megahertz to running a system at a frequency of 2 gigahertz. The difference is huge. The design complexity is also huge, right? So our discussion is related to that what will happen if we suddenly, hit with a higher frequency. So let's go ahead with the discussion. So here the terminology of power supply noise will come, but because I already mentioned what is power supply noise or supply noise, I'll slightly skip it. But here I think in this PPT, I'll try to get connect that why that transmission line kind of behavior comes into the picture in the power delivery network, which I mentioned, due to which actually the power supply noise is coming in the circuit. Then what are the problems available in the clocking system? And then we'll discuss what are the different clocking methodologies possible. Okay. Now let's talk about this particular picture. You see, I discussed about the DC line, or DC source. Ideally, we study like this. Think of another signal which is coming in this particular way. It is changing abruptly. Now, if you see for this, but the bottom curve, if you find the average value will be almost close to this only. Almost close to this, the top one. Why? Because here the value is VDD, but here value is quite lesser. So here also the value is quite lesser. So the moment if we do the segmentation and find out the average value, it will be coming like this only. The VDC will be somewhere here. So, but the point is we are going to see what impact it can give in the circuit. So these kind of voltage fluctuations are actually called supply noise or DC noise. Now let's go ahead and see how a particular chip and its electrical model is, which I discussed in the morning session also. See, you can think of this section as your pins or external pins. These are my pins, okay, which we are actually putting on the breadboard. So these are my pins. The point is, consider this red color is your chip. See, the red color is connected through some bond pads. From bond pad to these metal lines, we have some bond wires, and there are many different technology of connecting the ball wires, right? So from the external world, you have a long path to travel to reach the supply to the actual chip or actual circuit, and that is how we are actually going to get the circuit like this. You see, this is where the external world supply is. This is where the external world supply, okay? And from here, all these RLC, networks are there, and then we'll be connecting to the actual supply voltage, which is getting to the chip. Okay, so this is just an overview, which I discussed in the morning session, that why basically, and this section is actually called the power delivery network. This entire section through which the power signals or VDD is flowing. The same situation is happening from ground also. So you see, this is the real world ground, but actual ground is here. Okay, and that is the reason whenever we are talking about logic zero, we are not going to get at zero voltage. We are always going to get at some voltage like 50 millivolt, 40 millivolt, depending on your circuit requirement. I mean, it also depends on what is the total amount of current flowing through the, this particular circuit. What is this current? What is this current? This decides, because this entire current will also flow through the PDN, right? So the moment it flows through the PDN across R and L, it creates certain drop also. And depending on that drop, we actually can estimate what should be my ground potential, whether it should be 50 millivolt, 60 millivolt, or it should be something other, right? This is the same architecture which we can basically skip. So you can see this is the equation, this portion is the equation. The bottom line is it is R into IT plus L into DIDT. So that is how we are getting the voltage drop. Now, there are some important things. You see, because the supply noise is an R into IT plus L into DIDT, then what you can do is that you can either reduce R and L, still the value of PSN will get decreased. But the problem is this R and L are actually coming from these elements which are nothing but part of power delivery network. And as a circuit designer or as a device engineer, we are hardly bothered about this section. That is done by the material science engineers who build those paths, right? So in the as a circuit designer, what we can do? The only thing we can play with is IT and DIDT. So the vital factors as a chief engineer or as a VLSI circuit engineer is IT and DIDT. I mean, where we can do everything, whatever we need, right? Now, why this supply noise in the previous section also I discussed why it is so important. Right? Now let's talk about this particular example. Consider this is a D flip-flop or D latch you can consider. Here also you have another D latch, and for example you have some logic, some gate-based circuits over here, right? Now what is the final outcome of an PSN? Outcome of a PSN is if my supply voltage is for example 1.1 volt, which is 1100 millivolt, and for example due to the at the PDN my drop voltage or PSN is 100 millivolt, then actually in the circuit I am getting 1000 millivolt, right? 100 millivolt is lost. Okay. Now somehow, for example, that from the VDD to this particular D flip-flop, when I am getting the drop across, against the PDN, for example, the PSN is 70 millivolt, which means here I am getting, for example, 1030, for example, 1030 I am getting here, and for example, here I am getting 1000. So the problem is due to this situation, what will happen? Your first D flip-flop will be bit faster because we know in a digital circuit, scaling down of VDD has an just reverse impact at your delay of the system. Why? Because if voltage gets cut down, electric field will also reduce. If the electric field reduce, the drip velocity of carrier is nothing but mu into E, right? So electric field reduces means drip velocity of the carriers reduces. So eventually the delay will be more. So the situation is what will happen? This D flip-flop is working faster comparing to this D flip-flop. So what does it mean? It means the rate at which it is transmitting data, that is not the rate at which this particular D flip-flop can receive the data. So somewhere down the line, what is going to happen is if this continuously happens somewhere down the line, what will happen? That a few data may be lost in the process of capturing by the second D flip-flop. So these are the impact can happen in the timing front. Okay. This has a huge impact in the memory cell also. This architecture is nothing but a basic SRAM cell, okay, or static random access memory. So the problem is if the data, I mean, if the VDD line, because they are connected with the bit line and bit line bar. So if at certain line, your potential is different, at another line, potential is something different, then it will actually impact in the VTC of that particular, if you properly follow, the MOSFET works based, the SRAM works based on two inverters. This is one inverter, this is another inverter, right? So two inverters are connected back to back. That is the main thing. So for example, if VDD is different at two different inverters, the VTC of two inverters will be different. And if we analyze the static noise margin, read margin, write margin, hold margin, that will get disturbed because of the impact of PSN. The similar impact is also found in analog IC, mostly in the circuits like op-amp, analog to digital converter, mainly the mixed signal ICs. If the in the previous slide we have explained that the noise margin gets affected. If the noise margin gets affected, signal to noise ratio also gets weakened, right? So if the signal to noise ratio gets weakened, then in very tricky applications like biomedical applications, or for example in the IoT applications where your ADC and entire sensor hardwares are actually placed in, for example, outside jungles or rivers for the collection of data, where the interference of noise is more. If the noise margin gets reduced due to the more noise interference, their SNR will be very poor. And what is the resultant? Resultant outcome is we will be hardly able to detect the actual or required signal at the output. So those problems we are going to get. Now the point is, in terms of, in terms of the reduction of the PSN, what are the methods available? So here, all these, the traditional approach which I have segregated, these are all the approaches done by the persons who deals with the packaging, right? We as an engineer hardly can do anything over here. But there are some modern approaches where circuits are being incorporated. There are op-amp based circuits, there DIDT detector circuit, varactor diodes also people have used. And very recently, I think, from 2010, IBM proposed this concept of variable frequency clock. And this is where, this is the term I'm mostly interested in, that in this particular lecture, right? What is variable frequency clock? The moment clock we know, it means it is continuously fluctuating, having a same time period, right? A repetitive or a periodic signal. Now, variable frequency clock means, and this will be a repetitive or a periodic signal, but the period will vary over the time. For example, initially for a certain amount of time, it will vary as if your frequency is, for example, 50 megahertz. The next timing instant, it will vary as if the frequency is 100 megahertz. Then it will go to another frequency, for example, 200 megahertz, then 500 megahertz, like this. And it will reach to a maximum frequency at which your circuit should work. If your circuit is working at 2 gigahertz, it will reach to 2 gigahertz and it will get settled over there, right? So this is a technique people already have used. This is nothing new we have proposed. It is a technique already introduced by the IBM, right? Now, let's see what are different clocking strategies people have thought of. Now, see why or what is the problem. The problem is, I think I need to mention about something. Yeah, I need this particular equation to explain. You see, if we know the power dissipation, I mentioned in the morning section that power dissipation has few components: dynamic power, static power, and also leakage power, right? Dynamic power equation is alpha C VDD square F, where alpha is the switching activity, CL is the load capacitance, VDD is my supply voltage, and then frequency of the clock signal. And if you see here, depending on the frequency, it decides what power you are going to get, or it also decides what current going to flow, right? So if you increase the frequency, current will increase. If you decrease the frequency, current will decrease, and accordingly dynamic power will get hampered, right? Now think of the analogy in the morning class. In the morning class, what was happening is that suddenly we switched it on and a rush of current is flowing, right? Here thing is different. Here supply is always connected, but current will never flow if the design is synchronous. Because if the design is synchronous, then clock must hit. The moment clock will hit, then only current will start flowing. Okay. Now the point is, now just think, if the clock hitting is 100 megahertz, the amount of current it will draw. Now compare the frequencies 2 gigahertz or 4 gigahertz and think the current will, what current it will be drawing, right? Definitely current will be huge, right? From 100 megahertz to 2 gigahertz, it is almost 20 times, right? So your current will also be 20 times larger because it's a proportional relation between power dynamic and the. So this is where the importance is that because the moment suddenly clock will hit and the rush of current will flow, it is again the same problem which we have discussed. But the method is different. Okay. So during the transition, means when your device is moving from sleep to active or off to on state, during that time, you turn it on slowly, which means what you do, you don't give 2 gigahertz instantly. You give 100 megahertz. And after certain amount of microsecond time, you give 200 megahertz, 500 megahertz, whatever, as per your design requirement, right? So the initial moment or initial 1 second or 0.5 second, you can vary the frequency. That's where all the game is. So at the very initiation of the operation, what they are doing, they are not directly hitting the 2 gigahertz. They are giving a continuously changing frequency, and the frequency will get locked at the peak frequency at which you should work, which is 2 gigahertz, for example. So PLL cannot do it. PLL will only generate the frequency you need. Okay. So for that, you need to design a circuit, some circuit which will actually do this generation of variable frequency clock, right? So now I was discussing, now I was trying to emulate the behavior with a modern processor. What you are doing currently? When you click the button to turn your device on, this is how current starts flowing in all your cores. Exactly the same thing happens in your mobile also. If you have 4 core, which is called quad core processor, then current start flowing to all the cores. Okay. But our objective is, or the objective in variable frequency is that why at the instant of making it on, you are giving current to all the cores. Because, for example, the moment we make our laptop on, until and unless we are opening any application like Word file, or for example, a PDF file, or a video, or a browser, no activity is happening, which means no core is occupied, right? So what we can do is that at that instant when we are turning it on, we should not give current directly to all the cores. Rather than we can give it one by one. But this timing is very small. It is less than in the microsecond. Okay. So that will do the job. Because see, the instantaneous, the moment you turn it on, no, this is how the current flows. This is the current. Now, one thing you have to understand that in these modern processors or in these modern CPUs, the current which is running, no, it is in amperes, which is huge. And 50, ranging from 50 ampere to 200 ampere. I mean, depending on what core we are using. Now see, think of this peak, any single peak. At a very small time, peak is that much of ampere of current. And imagine the amount of DIDT you are going to get. That is enormous, right? So rather than doing it, can we do that the moment we will turn it on, the current will increase gradually the way I am showing. The first it will come to I1, then it will come to I2, then I3, then I4. Eventually, the flow of current will be like this. It will increase gradually. And if it increases gradually, your DIDT can be managed. Okay. So that is the main objective of this particular research. Anyway, clock, the terminology of clock gating, I'm not explaining much. I think we have discussed somewhere. In the clock gating, we are actually managing the alpha, because alpha severity square alpha basically decides the number of switching activity happening. And as I mentioned that uh, if we basically manage the input and output